Okay, sir. Good evening, all. Sir, shall I start the presentation, sir? Okay, sir.
Yes, yes.
Good evening, all. Myself, Bhakti Gurudatta Thali. I'm research scholar at Department of Chemistry, Mumbai University. I'm pursuing my PhD under the guidance of Dr. Rajesham Kamble, Professor, Department of Chemistry, Mumbai University. The topic of my presentation is entitled Exploring the Electrochemical Potential of Copper Cobaltate Cobalt Oxide Nanocomposite on Different Substrates for Supercapacitor Application. The outline of my work will include literature review of the materials which I've synthesized for my work, followed by its experimental section, then the results and discussion, and lastly the conclusion and a short bibliography. As we all know that nanomaterials can be made up of nanoparticles, nanowires, nanofilms, CNT, fullerene, graphene, supramolecular system, and so on, and they have found various applications in various fields of life, like textile clothing, information technology, healthcare medicine, food nutrition, energy environment, biotechnology, and agriculture. But my work focuses on energy storage devices, typically supercapacitors. Now I'm going to talk about the materials which I've chosen for my work. I've chosen two materials, copper cobaltite and cobalt oxide. As we all know that spinal structures are of tremendous interest due to their various applications in sensors, supercapacitors, and so on. Also, we know that metal cobaltite, that is MCO2O4, they offer better electrochemical activity, electronic conductivity compared to the single component oxides. They have also been reported in literature for applications like supercapacitors, sensors, and so on. The other material which I've chosen is cobalt oxide. It has excellent electronic configuration, good chemical stability. Also, it has been reported for applications in supercapacitor, catalysis, and so on. As the copper cobaltite and cobalt oxide have overlapping band structures and they have good complementary properties, it was reasonable to believe that coupling between these two materials will exhibit an enhanced supercapacitive performance. So now I'm going to talk about the experimental methodology which I have adopted for the synthesis of all the materials. Firstly, cobalt chloride along with urea and distilled water was autoclaved and calcined to obtain the cobalt oxide nanoparticles. Further, cobalt chloride, copper chloride along with ammonia water and distilled water was taken in the ratio 1:1, autoclaved and calcinated at 350 degrees Celsius further to obtain copper cobaltite nanoparticles. Thirdly, cobalt chloride, copper chloride, ammonia water along with distilled water in the ratio 2:1 was subjected to autoclaved and calcination to obtain the final hybrid copper cobaltite cobalt oxide nanocomposite. Further, all the three materials were confirmed by techniques such as FTIR, XRD, XPS, and SEM analysis. Now I'm going to focus on the results and discussion part. So we have done the FTIR analysis. This is the FTIR spectrum of all the three materials was done to validate the presence of functional groups, and it was employed in the range of 4,000 to 400 cm inverse. As we can see, figure 1A is of cobalt oxide nanoparticle, where there were two peaks seen at 555 and 651 cm inverse, which indicate cobalt oxide stretching and cobalt oxide bending vibration respectively. Figure 1B indicates copper cobaltite FTIR spectrum, in which there are two peaks, additional peaks seen at 1630 and 3400, which indicate HOH bending vibration and OH stretching vibration. In the final copper cobaltite cobalt oxide nanocomposite, the peaks which were present in copper cobaltite and cobalt oxide are also present in the final nanocomposite. In addition to this, there were two peaks seen at 821 and 1040 cm inverse, which indicate that the facile interaction has taken place between cobalt oxide and copper cobaltite. Thus, the synthesis of copper cobaltite cobalt oxide nanocomposite was successfully confirmed by FTIR. Further, we have done the crystallographic studies by using the XRD. So these three are the figure 2A, 2B, and 2C are the XRD spectrums of cobalt oxide, copper cobaltite, and copper cobaltite cobalt oxide. As we can see, there were peaks observed at different planes for cobalt oxide at 111, 311, 400, 422. And the rest peaks at different planes were for copper cobaltite. As we can see that in the final nanocomposite, the peaks which were present in cobalt oxide and copper cobaltite are present in the final nanocomposite. Also, the absence of impurity peaks that suggests us that all the materials are synthesized are crystalline in nature. Cobalt oxide XRD data is well matched with the literature with the JCPDS card number 011155, and for copper cobaltite it is 761802. Further, the morphological studies was done by FEG-SEM analysis. So figure 3A indicates the SEM micrograph of cobalt oxide. As we can see that irregular shaped morphology is seen for cobalt oxide nanoparticles, which is consistent with the literature. For the copper cobaltite particles, spherical morphology is seen. And for the final nanocomposite, that is figure 3C, we can see that there is a spherical assorted particles along with rod-shaped morphology. In the EDAC spectrum, cobalt, copper, and oxygen are well present, which suggests that the conformation of copper cobaltite cobalt oxide nanocomposite has taken place. Further, we have done the XPS analysis to understand the surface analysis and the oxidation states of all the elements present in the nanocomposite. Figure 4A indicates the wide spectrum, which has copper, cobalt, oxygen. Carbon 1s is used as internal standard, which is at 285.1 electron volt. Figure 4B is of cobalt 2p. Cobalt 2p is deconvoluted into two peaks at 778 electron volt and 792 electron volt, corresponding to CO3 plus oxidation state, and the other two peaks are for CO3 plus oxidation state. There are also presence of two satellite peaks for cobalt 2p. Further, figure 4C is of copper 2p. Copper 2p gives peaks at two prominent peaks at copper 2p 3 by 2, 931 electron volt, and copper 2p 1 by 2 at 951 electron volt, which confirms that copper is present in +2 oxidation state. Along with that, there are two satellite peaks for the same. Oxygen 1s is deconvoluted into three peaks, 527, 529, and 531 electron volt respectively, corresponding to the metal oxygen bonding which has taken place, specifically copper oxygen and cobalt oxygen. Further, we have done the electrochemical studies using a 3-electrode system and a potentiostat on two substrates. The two substrates which we had chosen were glassy carbon and nickel foam to assess the comparative electrochemical performance which we are getting. So our current collectors were prepared by using the active material carbon black and PVDF dispersed in DMF and ethanol. Further, they were drop casted onto glassy carbon and nickel foam. Further, it was subjected to drying under IR lamp, and testing was done on potentiostat using a 3-electrode system, reference electrode, working electrode, and counter electrode. And for the measurement, CV, GCD, and impedance were carried out. As we can see, figure 5A and 6A correspond to the cyclic voltammograms of all the three materials. Figure 5A corresponds on reading taken on glassy carbon, and figure 6A corresponds to the readings taken on nickel foam. As we can see that for the readings taken on glassy carbon, there is slight reduction.
Sorry to interrupt.
Yes, sir.
Yes, try to finish.
Yes. There were slight redox peaks seen for glassy carbon, but in case of nickel foam, proper evident oxidation redox peaks were seen. Also, we can see that for the composite, it was better oxidation and reduction, suggesting good supercapacitive performance, that is pseudo-capacitive. For the GCD, figure 5B and 6B are the comparative GCD curves, in which also we can see for the composite, it was maximum compared to the other two materials. Further, we have done the Nyquist plot, that is real impedance was plotted versus imaginary impedance. Here also we can see that the diameter of the semicircle for the composite was lesser in both the cases compared to the other materials, and slope of the composite was larger compared to the other materials. For the stability, further we have done the stability as well. So stability on glassy carbon was up to 1000 cycles, whereas on nickel foam was 3000 cycles. And for composite, it delivered 76% on glassy carbon and 78% on nickel foam. Lastly, the conclusion, all the materials which we have synthesized are successfully confirmed with techniques like FTR, XRD, SEM, XPS spectroscopy. Electrochemical measurements were also done to understand the electrochemical performance of the materials. On glassy carbon, the composite delivered 542.77 Faraday per gram, and on nickel foam, it delivered 683.72 Faraday per gram at current density of 1 ampere per gram. With respect to the stability, on nickel foam, it was up to 3000 cycle, it was stable, showing a retention up to 78%, and on glassy carbon, it was 76% up to 1000 cycles at current density of 5 ampere per gram. So this material could definitely act as an efficient material for future performance of high performance supercapacitor. These are the references which I've taken. I would like to thank my guide for his kind supervision guidance. I would like to thank ICCMEPR for allowing me to present my work. I would like to acknowledge UGC for providing SRF's financial support. And I would like to thank Analytical Laboratory and IIT Bombay for instrumental facilities. Thank you everyone for having a patient listening.
Good evening, sir. I am Munisha Mahajan, research scholar in Chandigarh University. I am doing my PhD under the supervision of Dr. Sanjeev Kumar. My topic of today's presentation is nanomaterials in renewable energy, innovations and prospects. Sir, what about, first of all, I will like to introduce about the nanomaterials. Nanomaterials are the materials engineered at the atomic and the molecular level, ranging from 100 to 1 to 100 nanometers in size. Their minuscule size grants them unique properties like increased surface area, reactivity, light absorption. These properties are tailored by scientists for specific applications, making nanomaterials incredibly versatile and powerful in various fields, including renewable energy. We are having different types of nanomaterials. Due to their different properties, we have nanoparticles, which are tiny particles with diameters typically ranging from 1 to 100 nanometers. Example, quantum dots, metal nanoparticles like gold and silver, carbon-based nanoparticles such as fullerenes, graphenes, nanotube cylindricals are carbon nanotubes, nanowires are ultra-thin wires with diameters in the nanometer range. Due to their unique properties of size, dependent, their physical and chemical optical properties different in the different particles, materials for their bulk counterpart due to quantum effects at the nanoscale. Their high surface area enhances reactivity, making them effective catalysts. Moreover, we can control their size, shape, composition, and customize their properties for specific applications. Now, about the renewable energy, because renewable energy is crucial for addressing global energy challenges, mitigating climate change impacts, and fostering sustainable development. So renewable energy sources diversify our energy supply, enhancing energy security by reducing depending upon the finite fossil fuels. So currently, as increasing of the deployment of the renewable energy technologies worldwide, driven by the declining cost and policy support, renewable energy not only helps in energy production, but also supports local economies for the job creation. Now, their nanomaterials play crucial roles in enhancing efficiency, durability, and performance across various renewable energy applications. In solar energy, nanomaterials like quantum dots and nanowires enhance solar cell efficiency. Nanofluids are used in solar thermal systems for better heat transfer. In wind energy, nanocomposites are used for lightweight and durable wind turbine blades, and nano coatings improve performance and maintenance. In energy storage, nanomaterials utilized in batteries such as graphene electrodes and nanowire structures, and in supercapacitors for grid level energy sources. Nanomaterials play a critical role for the hydrogen production technologies, offering potential solutions for a sustainable hydrogen economy. Hydrogen is versatile, clean fuel with applications in transportation, industry, and energy storage. Common methods for hydrogen production include electrolysis of water and reforming of hydrocarbons. Nanomaterials such as metal nanoparticles, metal oxides, and metal carbon-based materials are used as catalysts to enhance the efficiency of these processes. Using nanomaterials in hydrogen production offers several advantages. They provide high catalytic activity, leading to faster reaction rates and low energy consumption. They enhance stability and resistance to corrosion, ensure durability under harsh operating conditions. Additionally, nanomaterials.
Try to complete in 1 minute.
Okay, sir. Okay.
1 or 2 minutes.
Despite of the benefits, these are the challenges and the limitations. There are some challenges and the limitations of the nanomaterials. Safety concerns include potential health and environmental risks due to their small size and increased reactivity. Scalability issues arise in maintaining quality and consistency. Industrial scale production. Future prospects for innovations. There are exciting prospects and innovations in nanomaterials for renewable energy. We are seeing advancements in nanoparticles design tailored for specific applications, enhancing energy conversion efficiency, and developing next generation solar cells and optoelectronic devices. In conclusion, nanomaterials present a transformative frontier in renewable energy, offering unprecedented opportunities to revolutionize energy generation, storage, and efficiency. They enhance the safety concerns, scalability issues, and regulatory complexities. They also present opportunities for collaboration and innovation across scientists, industrial, and policy domains. By continuing to invest in research and development, responsible deployment of nanomaterials, we can pave a way for a resilient, low carbon future. Together, we can harness the full potential of nanotechnology to address global energy challenges and build a more sustainable world for generations to come. Thank you, sir.
Good evening, everyone. Today I'm going to present this my research work on enhancing corrosion resistance of epoxy coating using different nanofillers. I'm Dr. Nikhil Sharma from Thapar Institute. I'm a project associate. Our research group consists of Dr. Shruti Sharma, Dr. Sandeep Kumar Sharma, and Dr. Rajiv Mehta. Our origin of research is we are focusing on reinforcing rebars in concrete. Concrete has a porous nature, and it due to the aggressive and ions attack, the passive layer on the reinforcing steel is destroyed, due to which sudden premature failures of concrete occurs. And it costs, as we can see the data, it costs billions of dollars to rehabilitate or reconstruct these structures, which is affected by the corrosion. And not only financially it affects, but also environmentally it affects our environment, as construction of concrete or production of cement responsible for the CO2 emission in the atmosphere. Therefore, if any effort to control the corrosion in concrete would not only lead to persistent economy, but also for the sustainable environment. Out of various corrosion control strategies, our research focus is on epoxy coatings. Epoxy coating is generally a resin and hardener two-part system in which hardener act as a catalyst. Once it polymerizes, a strong film has formed, which act as a physical barrier for the external environment to the metal. In concrete structures, epoxy coated rebars is being used, in which the reinforcing bars is coated with the epoxy coatings, is a very effective and proven to be a very effective and reliable method in harsh environments. As we can see, if the quality of the epoxy coating is preserved up to 98%, we can reduce the 98% of the corrosion effect. Several bridges across the Indian Road Congress also suggest to use these epoxy coated rebars in harsh environments. But there are major challenges to quality control of these epoxy coatings. The biggest first challenge is the micro inherent pores presence in the epoxy coatings, which form during the manufacturing process, which act as a sites for corrosion or damage initiation for the on-field application. And challenge two is its brittle nature, which renders them formation of micro cracks and damage, which also results in the early occurrence of corrosion. To encounter these challenges, we use several nanofillers, out of which we are discussing which improve the uniformity or dispersion of the epoxy coatings leads to completely eliminate their defects. For example, montmorillonite, a naturally occurring clay, which is characterized by layered silicate structures, has high cation exchange capacity, is used as a filler for the epoxy coating. Similarly, halloysite nanotubes, carbon-based fillers like graphene oxide and reduced graphene oxide, a 2D carbon allotrope. In graphene oxide, GO contains oxygen functional groups, whereas in RGO is a reduced form of GO. And similarly, carbon-based fillers in CNT, it's a 1D carbon allotrope, which is rolled of sheets of carbon atoms. It's used to enhance the strength of the composites. Our proposed methodology, in our work, we nanomodified the epoxy coatings with 4 different fillers, like montmorillonite, nanoclays, naturally acting nanoclays with the 2 weight percent, and the carbon allotropes have a low concentration of 0.4 weight percent. Montmorillonite and halloysite is used 2 weight percent, graphene oxide, reduced graphene oxide, and carbon nanotubes is 0.4 weight percent. And all modified epoxy coatings compared with the plain epoxy coatings and the control samples and coated samples. Our complete study involves 4-part strategy, in which part 1 includes the synthesis of these nanomodified epoxy coatings. In part synthesis, we add the nanofiller in the epoxy resin and subject to the high shear homogenizer at 20,000 rpm for 10 minutes. Then it is subjected to probe ultrasonication for 10 minutes. Then after that, we add the hardener and subject to mechanical stirring for 10 minutes, and the coating matrix is ready and applied to the rebars. Then in part 2, we prepare the sample for corrosion testing. Left side, we complete a electric circuit in which coated rebar is center act as an anode, and the
Nikhil Sharma, try to finish in 2 minutes.
yes, stainless steel wire mesh wrapped around the rebar to act as a cathode, and it is complex. In part 3, it is connected to the power supply and subjected to accelerated corrosion testing. These results were evaluated by the non-destructive and destructive monitoring. And non-destructive monitoring involves ultrasonic corrosion current and visual inspection, whereas destructive is mass loss and residual tensile strength. In ultrasonic, the major part of this is non-destructive monitoring is ultrasonic guided wave monitoring, in which we take the healthy bar signal is the right side of the slide. The healthy signals with the initiation of the corrosion, the signal is degraded, and once the rebar is completely corroded, the signal strength is completely depleted. And this is the variation in all the samples, and we can see the ultrasonic signature of graphene oxide after 90. For example, for plain epoxy, we close the corrosion testing because after 41 days, their ultrasonic signatures were completely depleted. Therefore, the sample is removed from the corrosion. But for samples, either they continue for the 90 days or they are removed from the corrosion once their signature is completely depleted. In corrosion current, similar for the same monitoring period, the corrosion current is there, the least for the geo modified epoxy coatings, and for the plain epoxy coatings, it reaches up to 0.2 ampere in 41 days. In the visual inspection, we can see, for example, in 41 days, plain epoxy coated rebars is completely corroded, severely corroded, and we can see the coating is has white cracks around the surface. Whereas in geo, in 41 days, there is no corrosion spots, and CNT and MMT, we can see the several corrosion spots were there. From mass loss and loss in tensile strength, we can see the least mass loss and least loss in tensile strength was for geo-based coatings, whereas for plain epoxy coatings, mass loss is approximately half for the uncoated rebar. But here is the key point is, in compared to control rebar, plain epoxy coated has a highest mass loss in comparison to control, because the corrosion is uniform in the cross-sectional area in control samples, but plain epoxy coating rebars, the concentrated corrosion were there, due to which the highest loss in tensile strength was there. Overall, we can see that nano-modification can significantly extend the lifespan of infrastructure, therefore contributing to a sustainable and economical approach. Thank
Good evening, everyone. Myself, Suhriday Barman, a research scholar of Tezpur University, under supervised by Professor Bhakti sir. So, first of all, my topic is the evolution of hydrogen and oxygen through overall efficient electrochemical water spreading using zinc titanate perovskite deposited electrode. So for that, as we can see in figure A, a basic perovskite material structure has been shown. So, which is a perovskite oxide type material because it has become an alternative as an effective electrocatalyst in water splitting systems. So, as shown in figure 1B, we can see a water splitting setup by which we have done the experimental works. So, and in figure 1C, as we can see, the screw piece electrodes, which are used as the electrodes for the further volumetric analysis. So first of all, we have synthesized the material of zinc titanate using the Sol-Gel process, and after followed by the characterizations of the material. Firstly, the XRD analysis. So as we can see in figure 2A, according to XRD pattern, the peaks are quite agreeable with the conventional JCPDS file, and also the sharp and well-defined peaks in XRD analysis indicates a high degree of crystallinity in the zinc titanate material. And also we have calculated the particle size using the Scherer equation. It's about 29.03 nanometer. And we have also done the FTR and FTR spectra of zinc titanate between 500 to 4000 per centimeter, as shown in figure 2B. From this, we have it's clearly seen that titanium oxygen, titanium stretching vibrations are probably at the intensity peak of 1139 per cm, and at approximately 830 per cm is probably connected to the zinc oxide stretching vibrations. Also, SAM and EDX analysis also has been done. So as we can see in figure 3a, the same analysis has been shown, but unique morphological traits, including certain irregular forms, which is agglomerated in the presence of bigger particles. So after that, to investigate the percentage of elements present in the prepared nanoparticle, it is also has been done, and in which we have found that 30.99% of zinc, 32.66% of titanium, and 36.35% of oxygen is present. So after the synthesized of the material, we have deposited the material on the screw-piece electrode, which we are going to use for the volumetric analysis or water splitting. So as we can see in figure 4, the deposition steps of the zinc titanium material on FeSPC has been shown, for which first we have zinc titanium materials. First we have make a solution of zinc titanium materials. Then we have dipped the screw in the solution for about 2 to 3 minutes, followed by putting it in the vacuum oven for about 180 degrees centigrade for 2 hours. So after the deposition of this material on the electrode, we have also have done the same images of the electrode, in which we can see the nanoparticles deposited on the SPC. So using these deposition steps, we have prepared 3 different electrodes using different amount of zinc titanium nanoparticles using the following steps. So before going to the flow rate measurement, we have done the volumetric analysis for the different pH values. So in which pH values we are getting the highest flow rate. So for that we have done this for 4 different applied voltages at different pH values. So we are getting at higher pH values, at the higher applied voltages, we are getting the highest hydrogen and oxygen evolution rate. So for by this analysis, we have taken the further measurement of volumetric analysis for the flow rate measurement, and this analysis has been done for the 3 different electrodes that we have prepared earlier, and at different concentrations, and also with the bare electrode, that is, which is not deposited with the material. So as we can see here in figure 6a and b, that when we use the bare electrode, it comes to action after a certain voltage of 1.6 volt, as we can see in the small graph. Inside graph, we can see it is clearly visible that after 1.6 volt it comes into action. But when we deposited the material on the screw-piece electrode, then we are getting the flow rate at about 1.3 volt, starting at 1.3 volt. So when we use the bare electrode, the hydrogen and oxygen flow rate is lower then, but after using the deposition of the material, we are getting higher hydrogen and oxygen evolution rate, as we can see in the figures. But after increasing a certain amount of deposition material, that is after 1 mg per ml, if we increase 1.51 mg per ml, then we are getting almost same results for the 2 electrodes.
Try to finish 1 minute.
Yes. So after that, we have to confirm the durability of the electrode material. So for that, we have done this experiment continuously for up to 500 hours at an applied voltage of 1.6 volt, and I have taken only 1.6 volt and 2 volt as shown in figure 7a and b. So here we can see that the hydrogen and oxygen evolution rate with different cell voltages almost remains same during the whole experiment, with a deviation of ±5. So after that, we have calculated the hydrogen production efficiency also using this formula, and for different applied voltages, and we are getting almost 63.24% as shown in figure 8. So we can conclude from this analysis that first we have a oxide perovskite material zinc titanate is synthesized using Solgel process, Then the material is deposited on the iron screw-based cylindrical electrode using deep coating method for different concentrations. So by using the deposited electrodes, volumetric analysis has been performed using the water splitting setup, comparing with the bare electrode. And we are getting that after deposition of the material, the flow rate of hydrogen as well as oxygen has been increased as we increase the concentration. And the water splitting efficiency has been calculated and gives us a promising of 63.24%.
So my presentation is on transformative pathways in material synthesis from theory to real world impact. And the outlines are, so we will gonna discuss in this PPT about research objectives, bridging theory and practice, optimizing synthesis process, and applications. So if we talk about the significance, then the material synthesis and processing is very essential for advancements in scientific and technological fields because it provides the link between the synthesis methods and material properties, and as well as it is also useful for optimizing synthesis process for customized material. And moreover, it has numerous applications in electronics and medical devices, and as well as in renewable energies. And the research objectives are to examine the modern synthesis methods. And there are three modern synthesis methods, which are mechanical alloying, sol gel processing, chemical vapor deposition. And then we will discuss about the bridging theory and practice, which is very useful to understand how synthesis methods affect material properties. And then we will discuss optimized synthesis process to identify key synthesis parameters to improve material properties and functionalities. And there are also numerous applications in electronics and other various fields. So in bridging theory and practice, if we talk about the DFT, which is density functional theory, it stands for density functional theory. It predicts electronic structure changes based on synthesis conditions, and it guides optimization of precursor concentrations in CVD, which is chemical vapor deposition, for graphene production. And XRD stands for X-ray diffraction, which confirms crystal structure and the phase formation during synthesis. If we talk about this bridging theory and practice through example, then using density functional theory, researchers predicted the optimal conditions for synthesizing graphene via CVD. Practical experiments confirmed the theoretical predictions, leading to the production of high quality graphene sheets with controlled thickness and electrical conductivity. And so by bridging theory such as DFT, with practical experiments like XRD and to XRD, we can put insights into material synthesis. This integrated approach not only enhances our fundamental understanding, but also accelerates the development of advanced materials with tailored properties for diverse applications. In summary, integrating theoretical frameworks with empirical studies is very important for advancing material synthesis, enabling us to innovate and contribute to various fields of science and technology. So, uh, if we talk about optimizing synthesis process, then first we focus on parameters optimization. This involves adjusting synthesis conditions such as temperature, pressure, and precursor concentration. And secondly, we utilize advanced characterization techniques to assess material structure and performance. Techniques such as XRD SEM provides insight into crystallographic structure, morphology, and effects. So also there are numerous applications such as in electronics to develop high conductivity materials for faster and more efficient electronic devices. And there are also, it is also useful in medical devices and in renewable energy for enhanced material for solar cells, batteries, and energy storage systems. So in conclusion, our study underscores the critical importance of bridging theory and practice. This systematic approach has not only enhanced our understanding of material properties, but also accelerated the development of materials with tailored functionalities. So looking forward, our findings set a solid foundation for future research and innovation in material science. They open doors to exploring new material refining synthesis techniques and fostering interdisciplinary collaborations that will shape the future of technology and sustainability.